Okay, so today what we're going to do is we're going to talk about my latest experiments in computer graphics.
Whoopee! Sweet.
Yes, that whoopee is Reed. Hi, Reed.
Hi.
Reed's the only one here, but maybe next time somebody else will show up.
I'm special.
Yes, he is. He gets to be my guinea pig. Okay, I'm just positioning the camera. We got the boards. Okay, so what we're gonna do is we're gonna talk, about cellular simulation. Otherwise known as Caves V2. Okay. So 5 years ago, I came to Second Life, and I needed a home appropriate for myself. And what I decided to do was to build a cave system to live in. And it was pretty cool. I mean, it still is pretty cool. Here, I'll move the camera around and we can see what it looks like. It is concrete and it's made of blocks, and the paths go on for 7 miles. It's enormous.
And it was sort of an organic code, right? Like it grew itself, didn't it?
Yes. I'm getting to that. Thank you. It was the result of a genetic algorithm that was trying to maximize some criteria I gave for it. So that was pretty cool. That sort of makes up for the fact that it looks more like a maze than it does a cave. So what it is all these voxels. A voxel is a 3D pixel. So if you think of a grid, it's more or less a grid. All these grids are either on or off. Either they're a concrete block or they're not. And so I asked the program to give it special properties. Like I wanted the path to be as long as it could be, which ended up being 7 miles, which was nice. I asked for rooms. I asked for flat spaces for rooms because basically most of the time you spend standing on the floor, stuff like that. But it's flat. It's not very cave-like. But then, Second Life started working. Linden Lab started working on their meshes project, which allows for any sort of shape, not just prims. And I was like, it's time to make some much cooler caves. Public speaking and Carl. So, what I did is I got to play with one of my favorite ideas of late, which is cellular simulation. Where's my eraser? Eraser. There it is. Okay. Okay. You like my blackboard here?
Pretty sweet.
Thank you. See, I'm going to leave some of those letters up so it looks like a real blackboard.
There you go.
Yeah. It's pretty hot.
It's amazing what you can do in Second Life.
Yeah. So, what do I mean by a cellular simulation? I Googled around and I saw that people actually do cellular simulations, and it means something in the literature, and that's not what I'm talking about at all. What I'm talking about are basically particles. A particle in computer graphics is essentially just a point. It has a point and a size. although I'm going to give my points, my particles, orientation too, so rotation. But they don't have any sort of shape, really. They're not, so like some other sort of 3D shape might look like a cube. Particles are just a point. What makes them cells and not just plain old particles is the fact that I give them special rules to make them cell-like. And most important of these is I tell them that they can't overlap. Because if two cells were like that, or like that, or like that, that's sort of exactly the opposite of what I'm going for. So, rule number one is I want the cells to
repel each other?
Repel. And not repel each other a lot. Like, if we have them here to here, I don't want these guys to continue to push apart, you know.
So there's a limit.
Right, exactly so. Exactly so. I just don't want them to overlap. That's fine. So that's the first important rule with cells. And then the second is reproduction. So how do we get more cells? And that'll vary too. But basically what I do is if there's room around the cell, generally it's allowed to reproduce. So if we have two cells like this, one of these might reproduce and do like that, and we might get one up here. But if we were, say, constraining them to a box, you know, and we got another one in here, they might not. They might, at that point, they might stop reproducing, or they might pack it up a little bit better. And that's the general concept behind this cellular simulation. And the reason I think
so you can fill a volume with these guys.
Read. You've been reading ahead.
Am I jumping ahead?
You've been reading ahead. This just not.
Well, it's just I know from using particles in the past.
Oh, it's true. It's true. And you also, I did hint that I was going to be making caves with this. So,
yeah.
Anyway, the reason I like this idea of cellular.
Oh yeah.
Yeah.
Oh,
yeah. Yeah.
Yeah.
That's
cool.
I didn't tell you about the cave aspect beforehand, so
Yeah.
that was kind of a surprise. I was sort of hoping for an ooh or an ah, but that's okay. I didn't get one.
Well, you just got it. You
Okay.
just got it.
Okay.
Oop, oh.
But now I'm distracted. Okay, so the reason I like cellular simulation is because I think I can make really cool stuff with it. For instance, I just drew you that box, right? If, say, I wanted to put scales on this box, I could use what I just described to put scales on it, like this, say.
You don't mean fish scales.
I do mean exactly fish scales.
You mean fish scales.
Or
Wow.
reptile scales. I'm going to stop drawing these centers in a second. So like if I wanted to put scales on the box, I could, but I could then very easily also make it substantially more interesting by varying the size of these cells as we go up the box, right? So as you get up the box, then you start getting little cells. And then say up here, you get little bitty cells. So you can get variations in your texture that you can't simply get by tiling or any of the other tricks. And then also, because we're going to be simulating this in 3D, if, say, you needed these scales to grow onto your dinosaur, normally when you texture an object in 3D, you have to worry about how the...
It was quite the dinosaur.
Thank you. Thank you. I've been practicing with my Wacom tablet here, Wacom tablet. Normally when you would paint textures... Okay, so we had some technical difficulties. We're back. Thankfully our dinosaur came out unscathed.
Yes.
Yes. Okay, so I think what I was talking about was how if you had to texture paint on a dinosaur,
Yes.
the texture space would be all stretched out on the dinosaur, whereas if you simulated the cells constrained to its surface, then you don't get that problem, and you can do things like another sort of, I talked about scaling the size, but you could also say scale or change the orientation so they could well, that's a bad example. Let's say the dinosaur has an eyeball here. That's his eyeball. See, is that nice? You could lay down your cells like so. Make a nice little pattern like that. Anyway, the idea is that you can get fairly interesting and lifelike and not lifelike, but complex and cool patterns from simulating cells. And then you don't even need to, or you can have multiple types of cells, say, so maybe even the eye is a cell type, and there's another eye over here, and another eye over here, and then this, these, I don't know, skin cells, whatever, these scale cells grow in between, and then based on the forces, they line up correctly, but behave the way, you'd sort of expect, and, oops, well, I don't know.
So they're very smart.
They can do cool stuff. And it doesn't need to be, although they look pretty organic, you could say grow a brick wall this way. One of my friends back in the industry was obsessed with brick walls. He had to do a village or something, and he just wanted to lay down, here's my wall, and here's my wall, and fill it with rocks. So that sort of stuff too. So I saw this as a perfect opportunity to use this technique to build my caves and explore ideas which I thought would be a pretty simple cellular system, which is that of a circulatory system. So basically out from the heart comes a vein, and it branches, and it branches again, and so that's kind of cavey. So what kind of rules do we need for this sort of circulatory system? Let's change our rules now. So again, we want them to repel each other, and just so that they don't overlap, right? I don't care so much that they well, actually I do. For this, I let them repel each other over distances so that they would fill the space. If you have a vein going this way and it branches, these two should sort of push away from each other and try to go to places where there are no veins yet. So, maybe it would do stuff like this. So they repel. What's the next rule, Reed?
Reproduction?
Oh, reproduction. Let's not do that one yet. Wait, there are 4. I should have made notes. There's reproduction. Well, fine. Reproduction. Oh, yes, reproduction. So when a cell has no pressure from his neighbors, he'll reproduce, but he will reproduce with a connection. So say these two are connected, and these two are connected, and these two are connected, and these two are connected. So they repel each other, but they have a third rule, which is they connections are attracted, or connections. And we'll implement that via springs. So if we look at this as sort of a physical simulation, the repelling is sort of like an anti-gravity, and the connections are done with springs. And then is there another one? Oh, yes. And because Second Life is finite in nature, we're going to constrain this to a cube. That is not how you draw a cube, but this is. That's still not how you draw a cube. Okay.
There you go. That's better.
Yeah, still pretty bad. Am I going off the bottom of the board
so
here?
Constrain it. You mean constrain to a volume? It doesn't have to be a cube.
Yeah, no. Well, in our case, it's going to be a cube. You could constrain
Just
it
for simplicity.
Right. You could say constrain it to the shape of a dinosaur, which would be more interesting, but also harder to implement. But it's totally doable. And then you'd have a circulatory system inside a dinosaur, which is more lifelike, but not good for living in. What? What's going on here?
So you're planning on making cube version 2?
Yeah.
That's what this is all
Yes.
about.
Didn't you see the opening page was Caves V2? Yeah.
This is going to be...
Yes. Okay. So, when I first implemented this stuff, I did so. Okay, so one aspect of this class get-together thing is that, well, I'm going to talk about it ad nauseum and bore the crap out of you, but a nice aspect of it is that I am going to give you all of the code that I use to do this stuff so that you can play with it at home. That's not only highly encouraged, it's mandatory.
Yay.
What is going?
Yay.
What is going on here? Something weird. Oh. Okay, hang on. I have to get my keyboard out, but my keyboard. Oh. My keyboard is pinned underneath. I've got all these input devices here. Okay. So, I give you guys all the code. Let's go take a look at the code.
There it is.
Okay, I keep it in project. Cell. Is that a good name for it? So I need to clean up a bunch of stuff before I give it to you, which I will. There's a temp file too. But what I've categorized these into runs. If you look over here, I've got a bunch of directories, run 1 through run 13 now. These are the different, say, versions of the codes, different experiments I was doing to refine it, and the files they created. So, but before I broke it out into that, I put stuff in the main directory. The first thing we're going to look at is this Mel script. Mel is a scripting language for Maya, and it's how I first implemented the cellular simulator. So we've got a function for length, and a function for distance between, and normalize, and to duplicate a cell. I'm not going to talk about this hardly at all because guess what? Scripting languages are slow, and Mel in particular is obscenely slow and gets slower the longer the script runs, which is an interesting property that I had totally forgotten about and is really annoying when, say, your simulation has been running overnight, but it can only do like a frame every 2 hours now because your scripting engine has ground to a halt. So I quickly moved away from that framework. Yes?
And hence the C++ API, which is at least 7 times faster than Mel.
Well, it kept getting faster. It's a lot more than 7 times faster. Okay, so here we are in run 1, which I'm pretty sure was generated by C++. All these cell files are snapshots of the cellular system at different points in time. Cell.
So you can make a movie out of them.
Yes, so that is exactly right. Cell.cpp my file? Yes. Okay, so cell.ppp is my simulator. And it generates frames over time so that you can then save file. Oh, okay, sure. Why not? Who cares? Let me show you one.
You wrote this. You wrote this for Maya.
I wrote. Well, this isn't for Maya itself. This you can cells dot is it CPP? No, cell.cpp.
Yeah.
Cell.cpp. Yeah. Okay. You can compile. So if you guys want to use this code, you have to have a Unix-like environment. But if you want to compile it, you just say g++ cell dot blah blah blah. You see my crappy code, but it generates a dot out, which is the program. So that's all you have to do. You don't need Maya. And what it will produce, let's look at the first frame. It'll produce a file like this, which is the first number is how many cells there are, 2. And then the next 3 numbers is its position. The next 3 numbers is its size. The next number is how many connections it has. It only has 1. And the next 1 numbers is the things it's connected to. And then here comes the next cell, its position, its size, number of connections, and who it's connected to. Okay, so that's not very exciting. What's nice, though, is that we have code to read and write these files. Obviously, cell.cpp will read and write them, but also will load cells.mel. So say you want to visualize this stuff. You have this Mel Script. Look at this. Load cell, and you give it a file name, and it reads them in. And what it does is it creates spheres. So it creates a sphere, and then it scales it to the size, and it moves it to its position. And there's also a render cell, but I don't do that. And then down here, this is how you would do it. You would say load cell, and then you would give it. So right now we're loading from run 12, frame 100, and it would pull that up in Maya.
So basically the plugin is for Maya to read the information generated by your cell program,
right,
and build what it sees in the in the file.
Right. So yeah. So
you're a smart guy. You're a smart guy. You're a smart one.
Oh, thank you. You're sweet. So this is kind of boring. Let me show you something sexy. I'll show you the output. So here is the output from this thing I ran. It has all the rules we talked about. It also has an additional rule that is regarding size. Over time, cells get bigger exponentially. That's all. And I think, Reed, you've seen this. But this is...
No, I don't think I have.
Oh, you haven't?
I might have.
So...
I don't think I've seen the movie. I think you showed me a frame
of
the movie.
Oh.
Yeah.
Okay, so there's the movie. Here, let me put it on loop. So it's doing everything we said. I'll go look at the code, but this is basically it. If there's no pressure, it reproduces. They're connected. They grow in size over time. They're constrained to a cube. Zowie. Okay, so I wanted to show you this last, but I felt that things were getting boring, so I showed it to you now. Let's quickly go look at the code that does this. And that's in cell.
That is mega awesome.
Cell.cpp. Okay. I gotta slow down my voice because my display is a little bit slower. Okay, so we have a class called QVector that basically just holds 3 floats. You can construct it, you can ask its length, you can ask the distance between 2 of these, you can get it normalized, you can multiply it by a scalar, you can add them together, you can subtract them. Yeah, so I'm, I'm going to go over this stuff kind of fast. I apologize to those of you who haven't programmed before, but hopefully it kind of makes sense. And if not, you don't need to change this code, you just need to use it. Okay, so that was a vector. Here's my cell. My cell is also pretty simple. It has a vector which is its position, it has a vector which is its size, and then it has a set of integers which is who it's connected to. And then I have a global variable which is a vector or an array of cells. So this is all of our cells. Starts out empty. They're made up of the QCell class, which was made up of the QVector class. Add cell is pretty simple. It takes a cell and it adds it to the system. Duplicate cell is how we're going to replicate. It takes a cell and copies it in place. And then it takes a Boolean to say whether these 2 cells should be connected. Connect cells creates a connection between 2 cells. Oh, I know there is no disconnect cells. Oh well. Save cells does what you think. It saves it out to a file. Load cells does what you would think. It loads it from a file. Blah 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 blah. Okay, now we're getting into some fun stuff. Repulse. So this is the pushing apart of the cells, and what it takes is a position, which is the position of the cell you're asking about. You're giving it the position of another cell, and you're asking it for this cell's new position based on that other guy's position. Now I should talk at a high level. When I described the system before, you may have gotten the impression that I was going to do some physically accurate simulation involving forces and masses, and that is not at all what I'm going to do. First of all, cells, when they're growing, they don't really, like, if we were dealing with asteroids out in space, if it started moving, it would keep moving in the direction that it was moving. It would have inertia. But I don't want cells to have inertia. I don't want them to have acceleration.
You don't want them to move, really.
Well, I want them to move a little bit. Like if 2 cells are really close together, I want them to push apart.
Oh, well then,
right.
Push apart to a point.
But once they start pushing apart, I don't want them to keep moving, as if, like if you fired a rocket out in space, you would keep moving until some force pulled you back. I don't want that. I have grossly simplified the laws of physics, which is right here. In fact, I'm just going to gloss over it because there's not really anything terribly interesting about it except for the fact that it has the property, if 2 cells are too close together, it will move the first cell away.
And if power is greater than 1, you cut it off at 1. Just looking at.
Oh, see, your Reed's cheating. Oh, Reed. Okay, well, you failed this class.
How am I cheating? I'm just looking at the code that you have up there.
Okay, so it takes.
I'm just a good student.
It takes the distance between the 2 cells. If the distance is way too small, it clamps it to just small. L is the distance times 10. Why did I choose 10? I have no idea. Because it made the system work. Power is some kind of how much force is between these 2. So what we want is a function that when they're really close together, pushes them apart a lot, and when they're far apart, pushes them apart almost not at all. So what we do is we divide by this L. So if the distance between them is big, you're going to divide by big, and you're going to divide by big again, and you're going to divide, if you see, we divide by 4 times to the power of 4. Why 4? Well, because 4 is like 10, it makes it work. This is actually, if you were going to use like real physics, gravity is a squared law, so you divide by 2, but gravity is attractive, not repulsive. Magnetism is a power of 2, I think. I don't know about the others. But anyway, so we figure out the force, we figure out the force between them, and then its new position is, so delta divided by length is going to give you just the direction, the normalized direction. I didn't call normalized here, but you multiply by the power, and then you multiply by this constant repel force, and you multiply this constant time multiplier. And if we scroll up, we'll see those. Time multiplier is 5, and repel force is 0.001. And again, those are numbers that were pulled out of my thin air to make it work. The only other interesting thing here is that the function returns power. So this is a scalar, how much they press apart. We use that to determine how much pressure is on the cell later on for the reproduction step. So repulse moves the particle apart and then tells you how much pressure it was under from just one other cell. Okay. Simulate here. Okay, so a new function, simulate, takes the number of steps, which is nice. Simulate is the thing that produces the frames of animation. So you might have thought that since I pulled out repulse into its own function, I might pull out the other rules. I didn't. They're just in here in line. But we'll get to them. So simulate takes a number of steps. And if every 100th step it prints out something and it saves a file snapshot of it, okay, and then this for loop is the main simulation loop. It goes from 0 to the number of cells by each cell. So this is going to loop over all of the cells in our system. The first thing we do is we add a little bit of jitter, a little bit of randomness to the position of the cells. Because if, for instance, if 2 cells are at exactly the same location, which sometimes happens, then it sort of screws up the math. It just, adding a little bit of randomness helps the math, let's just say. Because like if they're exactly at the same position, then the force between them is kind of infinite, and the direction between them is undefined, and so the system deals with that. But to get out of that state,
it's like the deep thought problem.
It shakes it a little bit.
The physics engine of Second Life was having a few years ago.
Yeah.
When two objects occupied the same space at the same time.
Maybe.
And then they couldn't force themselves apart.
I should hope that the Havoc engine would be smarter than that, but
it wasn't.
Okay, so this will be our out position next frame. Okay, so new. Whoa, hey, don't erase the code. New position equals this position. Okay, so new position is going to be our position next frame, and now we need to figure out what it is. But it starts out at our original position. And what we do is we do the repulsive forces. Here's our pressure. Pressure is equal to 0. And what we do is we loop over the cells again from 0 to number of cells. So what we're doing is we're looping. So for each cell, we're going to loop over all the other cells. Oh, I got an IM in Second Life. Okay, well, you guys can. Welcome to Second Life. If you want to go to,
you missed the part where somebody was standing right next to you, telling you you're a pillar of awesome.
Really? Was there someone in here?
Yeah. Yeah, somebody was there.
I wasn't paying attention.
They were nice. They were nice, though.
Oh, that's nice. Sorry.
Yeah.
Sorry I wasn't paying attention, guys. Here, maybe I'm going to reposition the camera. I just looked down and saw that the position is bad. Okay. Oh. Hey, somebody's drunk driving with the camera. Okay, there we go. Alright, much better. Okay, so we loop over all the other cells. Now, the computer scientists in the crowd and anybody who knows anything about programming is screaming out in horror right now. But you know what? Screw you. I'll deal with it later. What we have here is known as an n-squared loop. Let's say, so what I'm doing is for each cell, I'm looping over all the other cells and computing the force between them. So if I have a system of, say, 10 cells, and say it runs at 10 seconds, say my simulation takes 10 seconds, if I then switch to 100 cells, well, first of all, let's look at it. If I have 10 cells, we loop over each cell, so that loops over 10 things, and then we have to loop over all the other cells, which is roughly 10. It's actually 9, but it's roughly 10. And we're going to hand wavy, so let's just say 10. We have to compute 10 other things, so that's 10 times 10. We have to do 100 things. Now, let's say that we move up to 100 cells. So 10 cells takes 10 seconds. Now, let's say we have 100 cells. We have to loop over 100 cells, and we have to do 100 things. What's 100 times 100? 10,000? Is it 10,000 or is it 1,000? No, 10,000.
10,000.
So we've got to do 10,000 things. So it's going to take 10,000 seconds. So going from 10 cells to 100 cells goes from 10 seconds to 10,000 seconds. You can see this is undesirable because we would like to be able to go from 10 cells to 100 cells and go from 10 seconds to 100 seconds. But instead we're exploding at an n-squared rate, and this is really horrible.
Exponential rate.
Quadratic rate. Yeah, exponential's worse. Bad. This is in computer science. If you ever see someone, if you ever see this symbol, come on. It's big O notation. It's O(n) squared. What we want is O(n). What we're going to end up with in the end is actually O(n) log n. And read, don't worry about it. Non-programmers don't worry about it. We're going to deal with it later. This is stuff I'll teach you as we go along.
Okay.
But it's kind of important for making efficient code. And computer scientists feel really snotty because they know about this stuff, and regular programmers don't. So when I teach it to you, you can knock them off their high horses. Okay, so let's get back to what we were doing.
So O(n) squared is bad.
O(n) squared is bad. O(n) to the third is even worse. O(n) to the n and factorial is really bad. Like if you've heard of the traveling salesman problem, it's like the worst problem in computer science. It's figuring out the shortest route between, say you have to visit n cities, figuring out the shortest route to get you to all n cities is order n n 2 to the n. Sorry, which is bad. And that's why now we have quantum computers, which Reed was talking about before. But quantum computers aren't going to solve the problem either. And it gets into P equals NP, which is, really snotty computer science. I throw that out so that the computer scientists who are bored at least have something to nod their heads at.
Think about, yeah. Anyway, back to English.
Back to English. So we computed the repulsive forces. Now we're going to compute the connection forces. So one of our other rules was they push apart, but if they're connected, they really want to stay together. And that's what's done here. Again, we loop over other cells, but this time we only loop over the cells we're connected to, which is a much smaller number. It's usually 2, sometimes it's 3, sometimes it's 1. We loop over them, and I'm going to gloss over this big time, but we do a very similar calculation. But this time we pull them together instead of push them apart. And the numbers, the magic numbers chosen here are, here's a 0.1, K. Oh, the magic number is in K. What's K? K equals D times D. Okay, so it's a distance squared. So this is more like gravity. This is very close to the spring function, the spring constant force thing. Which is total crap because I'm not computing acceleration or anything, but it is distance squared. Okay, whatever. Next, we lock it to the boundary. So boundary above was defined to be 1.5. So that's a cube of radius 1.5 or 3 units across. And all we do is we say, hey, if it's outside the boundary, then clamp it inside the boundary.
So this code automatically assumes that you're using a
right.
cube.
This section,
right.
This is the section that you would replace if you were using a dinosaur. And that is more complicated, but it's pretty easy. You just need a function that will tell you the closest surface on the dinosaur from you. So what you do is instead of clamping to a cube, you clamp to, if you're outside the dinosaur, you move to the closest point on the surface of the dinosaur, and if you're inside the dinosaur, you don't worry about it.
But how would you define the dinosaur?
Just, you would read in a dinosaur mesh. Yeah, but then you need a library, or you need to write the code to compute this closest point, which is non-trivial, but libraries exist, and it's a solved problem. For instance, if you were programming inside Maya, which I like to do, they have a closest point function for you. It's kind of slow, but whatever. I'm not worried about speed too much. So sometimes we reproduce. Here is pressure. Here's a lot of magic numbers. Pressure times 10 raised to the 9th power. If a random number is less than that and the number of cells is less than 400, then here's where we reproduce. And reproduction is we duplicate this cell. Oh, and we set its size because we're doing size business too. We set its size to the minimum, the small cell size, in case the cell we're reproducing is bigger than that. And we connect it to ourselves. And if, and this code would clamp the first cell 0 to the origin. So I think of the first cell in the system as the heart, because it's the biggest and it's, sort of
it will become the biggest
right.
over time.
Right. So, and here's the growing business. The size equals the size times 1.00001. Here's another magic number chosen because it works. And then main. So main for the non-programmers is what gets called first. If 0, So this will never happen. But sometimes if you wanted to start from some other condition, if you wanted to load your start condition from a file, you do that here. Otherwise, you just make one cell and you stick it in. This for loop is commented out. This stuck in 200 cells. But we don't do that. We just stick in one. And we call simulate a bunch of times, which is that function up there. And we're done. Yay! That wasn't so bad. No, don't save it. Don't.
I sort of get what happened.
Yeah.
But we'll have to see when I get a good look at the code.
Well, so I'm going to record this and put this on the net. You'll be able to go back and listen to, and I go over every line, kind of. You can look at it in more detail. Like if you wanted to, say, constrain it to a bigger cube, you could do so pretty easily. Or if you wanted to change the initial size.
Yeah, you could just go in and change that radius value to something larger.
Oh, coffee is good for you. Okay.
Reed was paying
Yes, he was. Yes, he was. Okay, so that's run 1, and we only have 12 more to do. Okay, so run 2. Did I make a README for run 2? No, I didn't. Good job, Carl. No README for run 2. Okay, well, I put READMEs in some of these that talked about what the difference is, what I changed. But I happen to remember. What I didn't like about run 1... Oh, let's open it again. Let's look at it because it's pretty eye candy. Spin. Everybody likes eye candy. Here it is. Okay, so what needs to be improved is...
Don't see it.
You will in...
Oh,
you'll,
there it goes.
Yeah. There's a 5-second delay. And I try to stop. I try to wait 5 seconds, but I don't. So let's look at it. Problems are, well, this is a bunch of balls, not a circulatory system. So we need to smooth this out into a single cave mesh, or circulatory system mesh. And the way we're going to do that is with metaballs, although I'm going to call it an isometric surface. Because, I like to use those words. But they're the same thing. Metaballs are a special case of an isometric surface, and in fact, we're not going to use any of the other nice properties, so we could just call it metaballs. But when you Google on the internet for a metaball library, you won't find a good one, but you will find a good one for isometric surfaces. That's issue number 1. So we need smooth surfaces. And issue number 2 is annoying me. You know what? I don't think I dealt with this stuff in run 2. I think in run 2 anyway, this is stuff we're going to have to deal with, so let's talk about it. If you look at the size of these cells, you notice they change size, but their size doesn't affect their distance from each other. That's not
true.
good.
They just grow up they start overlapping.
Right, they overlap. Well, when they're big, they overlap. When they're small, they don't even touch at all. And this is mainly a problem when you get into the metaball system, because when metaballs overlap, they get much bigger, and we don't want these guys bleeding into each other. I'm jumping ahead, but yeah, let's not jump ahead. So we need to deal with this space between. Okay. So.
And you can see how it's sort of filling up the volume of the cube.
Right. You know what? I think that's the first thing I did, is I tried to fill up the cube more. So what I'm going to do is, you're familiar with the diff program?
No.
This shows you the differences between two files. So I'm going to ask for the difference between run1 cell.cpp and run2 cell.ppp. And the difference between run 1 and run 2 is that the cube is bigger, and I allowed there to be it didn't stop at 400 cells. It stopped at 4,000 cells. Yeah, so you can see that I didn't do ISO services at all, and I didn't really do anything at all.
You just played with the variables.
Let's look at run 3. I did run 2 and 3 at the same time. So my modus operandi, this stuff takes a long time to run, especially because we've got that nasty n-squared loop. So I would let them run overnight. Run 2 and 3 ran at the same time. Okay, so here, let me clear the screen. Do that again.
And it doesn't look like you included any multi-threading.
Yeah.
Weren't we just yelling at people who did multi-thread?
Shut up. I did. I multi-threaded it at a higher level. Let's say I ran 2 and 3 at the same time. We'll get to multi-threading. Asshole.
That doesn't count.
In simulation 3, the only change I made was I adjusted the criteria for reproduction. I made the pressure less, so it's going to reproduce more because it'll reproduce at higher pressures. Yes. Okay, so let's look at the output of run 2. Run 2, do we have any JPEGs in here? No, do we have any PNGs in here? Oh, Carl. Well, how are we going to visualize this? We're just going to have to fire up Maya. Aren't we fancy pants? Okay, so let's fire up Maya. Really? I didn't generate any output from this? Okay, so all we've got are 2,000 frames of cells. Yeah, that's all we've got. You would say, hey Carl, why don't you be more prepared for class? And I would say, meh, fuck you. Oh wait, did I curse? Oh, well, don't let your kids.
You're gonna have to bleep.
Okay, so let's change our load cell program to.
This isn't meta reality,
right.
Carl.
Yeah, I'm not gonna take the time to bleep this shit. Okay, so load cell is a little program that I run to see the output of my simulations. It's the thing that loads up the cells in Maya. So I'm looking at run to frame 2000. Save it. Do I have a frame 2000? Run special RT run 2. No, I've got a frame 199. Damn it. Okay. Or 1999. Okay. So let's get some Maya loving going. Let's get rid of that. Okay. Okay.
It's working now.
Loading 1,121 cells. Oh, you're still 5 seconds behind.
Yeah, we can't see the
output.
Whoa. Yeah, we couldn't see the script editor.
Yeah, no, I didn't show that. I've got a little custom shelf button up here that actually pulls up load script.
Oh, I see what you're saying.
Okay, well, that's... Well, how did we change this?
That's only 103,000 birds.
Yeah, well, you know, spheres. Okay, so this is the output. Oh, I need to make this smaller. Still. Okay. Can you guys even see that? It's so low res.
Yeah. Yeah, I think so.
Okay, well. Okay, so that was roughly 1,000 cells, and run 2 had a bigger boundary box. That's what made this one different. Let's look at run 3 then. Let's just hope that run 3 has... run 3, I left the size small, but I changed the reproduction Ah! Okay, yeah, I remember I liked this one. Run 3 kept the box small, but increased the probability, lowered the pressure, so they reproduce in more confined spaces, and I thought this is pretty cool.
That is pretty cool.
Now we need to start doing our ISO services, our metaballs.
So we can make
So we can make these paths through my new home. I didn't figure out how long it is. So my maze right now is 7 miles. I would be curious to know how big this is, because this can pack in much more tightly than the cubes.
People will have fun for hours.
This is also sort of this is a way that I can ask Linden Lab nicely how well their physics engine handles meshes by giving them this mesh.
Oh my God, dude! I don't know what it'll do.
I sort of seriously doubt this will work, but we'll see. Maybe we can dumb it down. Okay. Don't save. Oh, don't quit, Maya. Don't quit. I need to keep you around because I'll probably have to do stuff. Okay, so that's run 2 and 3. We know that we like run 3. We like it when it packs in better like that because it looks better. So let's look at the differences between where'd my diff go? Diff between 1 and 4, say. Okay, so 1 and 4 doesn't deal with the pressures at all. 1 and 5 doesn't deal with the pressures at all. Run in 6 just runs it a lot. Oh, I'm just making the cube bigger, making the cube a lot bigger. Boundary is 4, so it's 8 across. Remember that I like 7. Oh, and now see, look at this. 7's got a lot of changes. Okay. Okay. So run. So run 4. Let's go to run 4. Run 3. Okay, well, you were asking me about multi-threading. This is how I multi-threaded. I ran a bunch of tests overnight. Run 4, 5, 6, and 7. Which all looked like different things, which some of them worked and some of them didn't. I'll leave it as an exercise to the reader to go look at them if you care. But at some point around here, I started messing with this, iso.cpp. ISO is our bad boy that makes the metaballs. So for this, I had to go out and use somebody else's. Hey, Reed.
Sorry.
No dogs allowed in the classroom. Okay.
Sorry about that.
Okay.
Yeah.
Seriously.
My bad.
Okay. Okay.
My bad.
All right. I don't want this to be a habit.
But it's a service dog.
Did I tell you the story about Lisa and her service dog and how we got to bring our dog on the plane with us and it rode in her lap? Because she got her shrink to write a letter for her saying she needed her dog. Because we got the idea from a Chuck Palahniuk, however you say his name, book, because he wrote about
Chuck Palahniuk.
Really? No.
Yeah, Palahniuk.
No.
That's how you say it.
Okay. Well, anyway. Yeah, it actually used to work. I doubt it works post 9/11 now. Or maybe they put your dog through the backscatter machine. I don't know. But if you Google for support animal, you'll see someone who took their miniature horse on a plane. Because I guess if you can get a doctor's note, you can bring... Oh, there's a gorilla, too. So, back to...
Anyway,
Yeah.
back to code.
ISO services. the ISO library. So I looked around for different libraries to do this for me, and I decided, let's see, do I have a makefile out here? Yeah. Okay, this is when I started using makefiles too. Reed, do you know about makefiles?
Yeah, they determine how your code's going to compile.
Oh, resize. Okay, so I also played around with my sizing rules, but then I stopped. But ISO here, we link with this library called Cgal, which I assume is computational graphics. Computational graphics? No. Computational geometry.
I was right about that.
Computational
right?
geometry algorithms library. What's that?
I was right about that with the
Yeah.
makefile, right?
Oh, yeah. You were guessing? Yes, no, you're absolutely right. It tells it how to compile.
Well, I mean, the problem is that most of the time I don't have anybody to talk to about this, so
Yeah.
I just assume that certain things do what I think they're doing.
Yeah. So if you run,
So that
if
was
you
my
run
assumption.
make at this point,
Use
it'll
the
try to
makefile
compile the code, but the code is apparently broken, and
Yeah.
I don't know why,
They're
but I don't care. Later on, I do fancy stuff with makefiles, so we need to look at them a little bit. Basically, all it says is if you want to make the program cell, you check to see if cell.cpp has changed since cell was made, and if it has, then you run this program. And then you check to see if you want to make resize, you check to see if resize.cpp changed since resize was made, and if not, you run this program, which compiles it, and ISO. Later on, I will use makefiles to do renderings. And the reason is I'll be able to use all my cores that way for your multi-threading. So,
Well, that's my idea on the multi-threading.
well, you complained about multi-threading, so now every time multi-threading comes up, I'm gonna.
Actually, it's not even Maya doing multi-threading, because Maya doesn't multi-thread, Monterey does.
So I use the Cgal library. I need to talk about Cgal for a second because it's pretty fucking cool. I tried a bunch of different libraries, had mixed results. Cgal is badass. So in I keep wanting to say computational graphics, but it's computational geometry. So in computational geometry, a lot of the time you have problems because you're using the computer's floating point numbers to represent numbers, and floating point numbers aren't exact numbers. They're exact for like the number 3 or for the number 7, but they're not exact for the number pi, and they're not exact for the number 1/3. Most of the time in
That's because pi is an imaginary
well,
number,
it's
and,
not
and
transcendental is the word
1/3
I'm looking for, but
is
repeating.
What is the word?
Yes.
Repeating.
It's a rational number, but it's repeating. So irrational numbers, repeating numbers, but that's okay for most applications in computer science. Nobody cares when out at the 100th decimal place something changes. It turns out, though, in computational geometry, the algorithms are very sensitive to this stuff because if, say, you have 3 lines in 3-dimensional space, you typically represent them by a point and a slope. Those slopes are usually numbers like 1/3. If it goes down 1 for every 3, that's 1/3. And if you want to test whether these 3 lines intersect each other, you need the exact number. If you've ever tried to use a piece of software to do mesh Boolean operations, like you try to subtract a dinosaur shape from a cube, if you know what I mean. Do you know about? Yeah.
Yeah.
They
Yeah,
tend to
yeah,
not
yeah.
work at all, ever. Like they'll work for simple shapes, but for really complicated shapes, they don't work. They break down, and it's because of this rounding at the very lowest level. So Cgal has a numeric type which is exact. It's symbolic. So instead of storing 1/3 as 0.33333, it stores it as 1/3. And it's sort of, instead of storing pi as 3.14159, blah, 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 it stores it as pi. And it has, like, cool rules for dealing with this stuff. Cgal, as a side, I don't know if it handles pi right, but it does handle irrational numbers right. So if you're looking at distances, the square root of 2, distances from the center of a sphere, it handles that right. But that means it's obscenely hardcore and difficult to use. And we're going to see that in a second. But being hardcore and difficult to use means it's really good. I got fed up with it a bunch of times while I was working with this, but in every instance it turned out to be user error. They never let me down. So, let's look.
By user error, you mean your fault.
Bad. My bad.
Your bad.
So, Cgal. We have. So this is the code that is going to read. I guess I should talk about what it does. This is the code that's going to read the cells file and produce a mesh, which is an isosurface of the metaball system of that mesh, if that makes sense. So this is the stuff you need to know about to use Cgal. You need a default triangulation. You need a complex 2 in triangulation of 3 space. You need a geometry traits, which is a collection of things like your type for sphere representations and point representations. FT, I don't know what it stands for, but it is this is the magic number that that has all the precision you need. I should also point out that you don't get this magic precision for free. It is much less efficient than using traditional floating point numbers. Blah, 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 blah. Okay, so then we get into the vector stuff, which is the same as it was in the other program, because we're doing all the same stuff. There's the cell type. We have the same cell type. We have the same load cells, the same save cells. If I weren't being so sloppy here, I would put this into a library and reuse it, but, hey, we're sloppy. Here is the first important difference. This is the sphere function. This is the thing that does the metaballs. Let's skip it for now.
Let's skip
it for now.
Okay.
We're going to go down into main. Main is the thing that does most of the work. Okay, so I stole this code.
Main's the staple. That's all main is.
I stole this code wholesale from their isosurface example code. So if you look at their example code, it looks exactly like this, but they, instead of doing metaballs, they did a sphere. They did one sphere to show off their code. Oops. And that's why that function up there is called sphere function. I didn't even bother to change it. So blah, blah, blah.
Copy and pasting, Carl.
Yeah.
Copy
In fact,
and
their
pasting.
code didn't generate an output mesh. Okay, so here's the important line of code. Make surface mesh, blah, 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 blah. Well, here's criteria for this is how accurate it is. Here's the sphere function. Okay, so this is the function that we're going to replace. It gets passed in. It gets put into the surface. It gets passed in. Then we create a polyhedron. Because these things aren't polyhedrons, it outputs a triangulation. We convert the triangulation to a polyhedron, and then we output it as a wavefront OBJ file. Yay! And we print that to standard out. Okay, so let's look at this sphere function. Sphere function. Okay, this is going to take some of this stuff, some mathematical hand-wavy stuff. Okay, Reed, did you take algebra in high school? Did you take calculus?
Yeah. No,
Okay.
I didn't
Did you
take
graph
calculus.
functions at all?
Yeah, like y equals mx plus b.
Exactly. Okay, cool. That's all you need to know. So here is an axis. I guess you'll see the axis in 5 seconds. You know what? I need, well, whatever. Here is the axes. So what an isosurface is it takes a mathematical function, like if you say y equals mx plus b, that is the equation for a line. What the isosurface will do is you give it that function, and it will create a surface which is that function, that is that line. Okay, so
Okay.
it's like,
But how do you make a surface out of a line?
well,
That's a
right.
one-dimensional.
So we need to include z, and what we do is we define a function on 3 variables.
Oh, so we need to compute
Well,
x, y, and z.
What we do is, we define a function on 3 variables, and this equals a bunch of blah 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 blah. And the important thing is, let's get rid of this, and you guys are 5 seconds behind. The important thing is this. So this function takes in x, y, and z. This function will return a number, a single number. If the number is greater than 0, you're inside. If it's less than 0, you're inside, and if it's greater than 0, you're outside. Okay? So you can imagine how you might write this function for a cube. If you wanted to define a cube like this, you would say, well, if x is less than 1 but greater than -1, and y is less than 1 and greater than -1, and z is less than 1 but greater than -1. Did I say that? No. Whatever. It's inside, and otherwise it's outside. You could make a function that encapsulates everything you need about the cube. And if you pass it to this code, it'll make a cube for you. And it's exactly like how those calculators graph those functions for you. It just traces along the surface and does it. Does that make sense at all? Yeah? Okay.
Yeah.
So what it does is it literally traces along the surface, looking at points nearby, and if they're inside or outside, it changes where it's looking, and it draws the surface. And in fact, a very popular version of this algorithm is called the marching cubes, which basically starts building cubes. It starts asking about points, whether they're inside or outside, and makes cubes for them. If they're inside, it makes cubes, and if they're outside, it doesn't make a cube. And along the border, it makes these cut cubes, if that makes sense. But we're using something substantially more sophisticated than marching cubes, which gives us better output, and it uses triangles that look nice. But the main thing I want to say here is we need to define this function for metaballs. If we define the function correctly for metaballs, it'll trace our surface for us. Okay. So how do we define a function for metaballs? Well, what you do here, Okay, what you do is you go to your web browser and you
Google.
Right.
Metaballs.
So there are a variety of good functions for this. I didn't use any of the good ones. I used the one I made up from the top of my head, which works. And it is this. So this function needs to return, our function needs to return 0 or 1. And P is the point that we need to evaluate. So field is the number we're going to return. We're going to loop over all the cells, and we're going to compute the distance of this point from the cells. Okay, and if the distance is small, we're going to return a big number, and if the distance is large, we're going to return a small number, and at the end, we're going to subtract 1. Okay? Does that make sense? Okay, so specifically, we're going to take the distance, we're going to take the size, all right? We're going to take the size of the cell.
Yeah,
We're going to divide by the distance. Okay, so if if the cell is 1 unit across, and we are 1 unit from it, we return 1, and then we take POW 7. POW takes that, so that's the number to the 7th. Do you know what POW does?
No,
that's essentially that number to the 7th power. Man, my handwriting's bad. I just need to take a moment to make it better. So here is another. Here. There you go. Maybe from one of these you can understand what I'm
X to
yeah right.
X
I'm trying to
7,
say that
I got it.
in my broken way. This thing's commented out, and that's all we have to do. So, and then we subtract 1 to get it less than 0. Well, this is one of the general metaball functions, and what this has the nice property of doing is when you're not inside 2 cells, but you're close to 2 cells, the field, the numbers they spit out might not be 1, but they'll both be half, say, and they add together and they make 1, and then you subtract 1 and you get 0 again. So that allows metaballs to sort of merge.
Merge?
Does that make sense? You said merge, so you seem to know where I was going. Okay,
Yes.
cool. Okay, cool. So that's how the math sort.
Well, if it's 0, that means there's 0 distance between
Right,
the 2
so-
points, so it allows them to merge. I get it.
Okay. That's not quite right, but okay. Sort of. Sort of. You kind of got it. So that's our metaball function. Screw this crap because we want pretty pictures. Let's see. Run to star.obj. No. So these output things to obj files. 3.obj, no. Run 4.obj, no. Run 5, no. Oh, I was doing them out here in the root directory at that point. I hadn't moved them into the runs yet. So there are no OBG files. Yes, 7 was my favorite, so we see that we have a lot of runs for 7. And because I don't care so much about the other ones, let's just look at these. So,
Oh, I don't. Yeah. No, never
What's
mind.
that?
Sorry. Nothing. I was gonna say something that was
Off topic?
totally, irrelevant. Yeah.
Okay. So let's go into run a little.
Not necessarily off topic, just irrelevant.
Okay. Okay, so we've got this. What did I call them? Call them blobs or something. Date modified.
Yeah.
Where did they go? Okay, let's sort by name instead, because this isn't getting us anywhere. Okay, so let's look at these.
Blob cells 10,
Yeah.
100.
Let's look at that guy. See what that looks like. Ah, okay. Look at that. We got something that is not spheres. It is, in fact, a blobby sort of mesh. That's for frame 100. Import. Okay, now we want to see something better. I guess we could do frame 105. That would be really cool, wouldn't it? No, 105 isn't much better than 100. Let's do...
How about 1250?
Okay.
Wowzers. That looks amazing.
Yeah, that's kind of cool, huh? Okay.
Yeah, that is
but I'm going to show you a problem. So now we've got a new problem.
It's actually less polygons that way as well. It's more efficient. Way more efficient.
This is what I don't like. My tunnels are blobbing into each other. You see what I mean? Now, you were just saying that's fewer polygons, so that would be better, but actually that's not what I want. So, although this is cool. I hear what you're saying, and this does have really cool properties because it's very organic looking on the inside. But I want real tunnels because what I really want is a circulatory system because I'm doing cellular synthesis, and the circulatory systems don't have these big chambers. Well, I guess that could be the heart, but not what I'm looking for. But because we've been very short on eye candy here, and this is getting extremely tedious, I feel, I want to show you what this beast looks like growing. Oops. Okay. Oh, wait. Do I have a spin in here? Well, oh, I do. Okay. So the first thing I did was, because rendering this stuff is kind of hard, I took frame 1200 there and I spun it to see what it looks like. And I also made it, rendered it as, I wanted it to look like a electron microscope. So I rendered it just with ambient occlusion. And it looks like that. And that's I like that a lot. But like I said, I wanted to get individual chambers. And one of the problems with this is, as I discussed before, the size. The size isn't affecting the distance. So my next thing then was to simulate all those frames. So that's substantially harder to render, but we've got all the frames. Here is run 7 growing.
Oh, that's neat. That's really neat.
Oh, I remember what I don't like about this one. As it's growing, it might be hard for you to see with the current frame rate. The size of the cells is popping. They're getting bigger in discrete chunks. And that's because for a while I changed the size code to not be just grow exponential over time. It was a function of how many cells were downstream of it, if that makes sense. So I thought that would look better than the growth, but it caused this popping, which is both interesting but not what I wanted. So I changed the growth back to exponential. Okay, so oh look, we're halfway done, Reed, and we've only gone on for what, like 10 hours? Maybe we'll have to edit this seriously. So my goal then was to split these out and not let the veins, for lack of a better word, the tunnels, overlap with each other. I want the adjacent cells to merge with each other, but I don't want them to merge across across to each other. Does that make sense? Yeah. So we need to change our math a little bit. We also need to address that heinous runtime problem that I was talking about, because I want it to be more complicated than that. I want it to be a lot more detailed, and if I remember right, those, just to simulate the cells was taken like an hour, and then it was taken an hour to generate each mesh, each OBJ file from the cell file. So both things were really slow, and again, it's because of that n squared thing. Yeah, let's dig into that. Well, let's dig into the... Which one are we going to dig into first? I know. Okay. So... ISO. It's in ISO. And run... Was it around run 8 that I was dealing with this stuff? I don't know. Let's see. No difference. No, wasn't. Here we go. We got some changes. Let's look and see what they are. Oh, I was having problems with the meshing. Oh, no, here it is. Cool. Okay. So in run 9, I started dealing with the connectedness. I didn't want the nearby tunnels to merge with each other.
Yeah, that's what was causing all those big, huge blobs to occur.
What's wrong with this? eiso.cpp. Okay. Okay, so my idea was, in that mathematical function, if you remember, we added a little bit of metaball value for every cell in the world. My idea to keep them from overlapping is to do the following. Find which cell... So what we need to do is we're back at that function where we have to return 0 or 1, or numbers less than 0, or numbers less than or greater than 0, whether you're inside or outside. What we're going to do is we're going to find the cell that's closest to that point. Okay? So, and then what we're going to do is we're only going to add in the mathematical value goodiness for that cell and some number of cells that are connected to him. And all the rest of the cells aren't going to get to contribute to the shape at all. And that's going to keep them from blending into each other. as much. So
As
that'll
much.
keep adjacent cells from, that'll let the cells that are connected to the closest cell merge, but not cells across the void. So what we do is we cycle, so we get our point, and we find the distance to each of the cells, and we find the closest cell. That's easy enough. We get his distance, and if he's closer than the closest cell, then now he is the closest cell, and voila. The next step then is to compute the cells that are connected to him. And what we do is we look at cells that are within 2 hops of him. And we do that by looking at his connections, and we add the cells he's connected to in, and then we loop again, and we add in the cells that they're connected to again, and we loop again, and we add in the ones that are connected to them. So that's not that complicated. And then we go back and we do that math that we had before, but instead of doing it for all the cells in the world, we only do it for the cells we found that were connected. And it turns out this was enough to do exactly what I wanted. My next step after this was to put up little subtractive walls between cells that weren't connected, but I didn't have to do that. So this was enough. Let's look at the output from this, shall we? Yes. Do we have a... Oh, we've got a spin.move. Okay, well, let's just jump right to spin.move. We don't even have to fire it up in Maya.
Somebody's here saying that you can
Really?
have their babies. Yeah.
No, you're supposed to offer to have my babies for me. Otherwise, it's it's not. Yeah.
Not gonna work.
Soup. Say again. I'm sorry. I'm teaching class here. Can you come back later? And then we can talk about the babies. Okay. All right. Okay, so here is my run for not connected cells. Let's spin it. Da, 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 da. And it looks similar to the old one, but you notice the big chambers are gone. You still have big chambers, but that's just because the cells are so damn big. They've been around for a while. And let's see, the important thing to notice right here, let's see, let's wait a little bit while the video gets to you. Okay. If you see down at the bottom in the corner there, you've got this big blobby chamber and a little vein sort of thing sticking up into it. Do you see that? Before, that would have totally, those two would have been blobbed it together. Oh, there's a little vein growing down into it too. But now, because of this closest point thing and only taking the cells that are connected to it, veins will cut out space into other veins that they're not connected to. And that's what we want. Okay. But again, I wanted it to be more complicated than this. I wanted it to have more cells, and I wanted it to render. I didn't want to take weeks to generate this stuff, which is kind of what we're looking at now, because this stuff is getting slower and slower and slower. So the n-squared problem is bad, because as things get bigger, it gets slower, not exponentially, but bad, quadratically. Yes. So what we need to do is now we're going to use some full-on computer science, although it's kind of the lamest version possible. We need to find a way to find cells that are next to each other without cycling over all the cells. And the reason we want to do this is because cycling over all the cells causes that n squared problem. Hey, it wasn't letting me erase for a second there. And there are a variety of ways of doing this. There are KD trees. If you want to Google around, KD trees are nice. There are a variety of tree structures that will allow you. So basically, when you want to do searches fast, you use a tree of some kind. KD trees handle three-dimensional or n-dimensional structures very nicely, but I didn't know how to get them to work with my cells, given that my cells have different sizes. Because I don't just want the closest cell to me from its center, I want the closest cell from its surface. So I didn't use KD trees. There's got to be a way to make them work with sizes like this. Instead, I went with a voxel solution. You know, I just heard you yawn.
Oh no, I'm just tired.
So
How did you hear that? I wasn't like.
Well, obviously Skype is sensitive enough that it allowed you to. It told me. A voxel is just a fancy word for a three-dimensional pixel. Here I'm showing you two-dimensional pixels because they're easier to draw on the blackboard. But the idea is, if you want to find the cell that's closest to you, don't look at all the cells. Look at just the cells that are like, hang on. Right, you can seriously speed up your search by breaking things into a grid and just looking at the grid points, because grid points are an array and you can jump to any space in an array quickly. So if the star was our point that we're trying to evaluate, we don't need to look at the cells that are way over here on the side. We know that the closest cell is going to be either in the voxel that the point is in, but there are cases where the point you're looking at and the cell you're looking at might be like this. So like, say that's your voxel and your point is right there, and your closest cell is actually in the next voxel, not in your voxel. So not only do you have to look at the voxel you're in, you got to look at your adjacent voxels, and then depending on how big your cells are, they might cover multiple voxels, but that's okay. It turns out that if you loop over all the cells once at the beginning and stick them into their voxels, then when you go to find the closest cells, it's much, much faster. And it's pretty easy to implement too. KD trees are a little subtle.
So that solves the
Yes, it does.
n squared problem.
And then where did I do that?
Why didn't you just
I did.
think of that in the first place?
But you know, you got to implement this in order. You know, you can't do everything at once. And I didn't want to implement it if I didn't have to. Like, if you remember, I started with Mel at the beginning. I didn't want to move to C++ unless I had to, and it turns out I had to really fast. Okay, so the difference between, so run 9 was the good one. Let's see if we got into the voxel crap by run 10. No, run 10 was exactly the same. I think it was run 11 and 12. Run 11 is the same. Come on. And there we go. The difference, see, we've got all kinds of voxel stuff going on. Okay, so let's look at that guy. See, now, don't you like diff? Isn't diff nice?
Yeah, diff is
This is
nice.
why I work in the command line. It's because I can do stuff like this really easily. There's probably a GUI thing to
Yeah.
do this, but
Well,
whatever.
yeah. That's what I was gonna say. I like my pretty GUIs. I guess
Well, I'll
it's
show
not
you a trick
hardcore
in a
enough.
second that I know your GUI can't do. So, ha. But what we have here is the voxel table. I set the size of the voxels to be 0.27 because I wanted them to be bigger than the biggest cell, but as small as they could be. I actually implemented the voxel table itself not as a vector array, but as a hash table. So I could look up coordinates via hash.
So what's
A hash table is a dictionary. It basically lets you. It's like an array. Okay, so it's like an array, but instead of putting an integer number in, you can put anything in, and it maps to something else.
Oh, okay. So it's like a
Maybe.
tuple or whatever. From,
Maybe. Not sure.
okay.
But it lets you look up anything. It's not as fast, but it's still pretty damn fast. And in our situation, it has the advantage that voxels that don't have anything in them don't take up space. It's space efficient, so it'll wrap itself. In fact, the first time I used this structure was on the matrix. Reloaded, I needed to store atmosphere, the number of water particles in the atmosphere to render the swamp gas, and the swamp gas at the bottom of the tunnels doesn't fit inside a cube. It takes up a lot of space that's kind of arbitrarily shaped, so I used a voxel table instead of... Okay, so I just thought I would name drop there. That usually gets people excited too. Right.
Yes, I worked on
Luckily, your audio just cut out, so I don't get to hear all of your mocking. Yeah, perfect. All of the mocking just got clipped right out there. Okay, so I used a voxel table. Query voxel table neighbors. So I'm guessing, given a position, this will find. So it loops over -1 to 1, -1 to 1, -1 to 1 in X, Y, and Z. Finds them. In our sphere function, the only change we make is that instead of looping over all the cells to find the closest one, we only loop over our neighbors in the voxel table, and we have to handle the case. Now, we might not find any neighbor at all because the voxels in our neighborhood might be completely empty, so we just need to handle that case a little carefully. It's not a big deal. And then our generation of the OBJ files increased by a factor of 50. It went from an hour to a minute, and that allowed me to add many more cells.
Sweet.
Yes. And then the only other change I made here wasn't in run 12. Yeah, it was. Wasn't it in run 12? What? Run 12. Maybe it was in run 11. No. Did I put in back in run 7? No. Run 9? No. 10? No. I just looked at 11 and 12, didn't I? I know it's in 12. There it is. Remember I had the makefile that would compile my programs for me? Now, not only is it compiling programs, it's generating my OBJ files. So up here I have a generic rule. You can make an OBJ file from a cell file by running the program ISO on the cell file and produce the OBJ file. And then down here I have a list of all my OBJ files I want to make. Here is the fancy pants command line program you run to actually make this little bit of the make file. Could never have done that with a GUI. And the reason I do that is because now I can do make-j5 OBJs, and make will handle the farming this out onto my different cores. So it's multi-threaded. Yes. So now I can, now in addition to generating these in a minute, it can generate them 8 per minute because on all the cores. That gets lost because that gets lost because I started adding more cells, which slowed it down again. Okay, so let's look at what this looks like. Back in our friendly neighborhood Maya. Load cell. Okay. Cells run 12. Let's look at frame 1500. Load that for me. So what I've done here is I've increased the size of the boundary a bit, so that I get increased numbers of cells and increased complexity. And
loading.
Yeah.
38.
Yeah. So it's not a lot more. I was doing around 1,000 before. It's only 4 times more, but the space is 4 times bigger, and then you get. So you get something that looks like this. And you get the, not run 7, please. Where are we? Run 12? Run 12. Let's just scroll down and import it. So just to recap, the cell program generates the cell files. The ISO program generates the OBJ files. There's a little Mel Script back out in the main directory that loads these and renders them to make an animation, and then you stitch those together into a movie. Okay. There is. There's what he looks like. Yeah.
It's not too bad.
And then get rid of.
Whoa. That's cool.
And then okay. Shh.
The only thing I see as far as getting. All right.
You want
Sorry.
to? Yes, you want to watch this.
Silence
So this is the pinnacle of all of this work.
It's like a virus or something growing, or a bacteria.
Well, I like to think of it as a circulatory system. But yes, it does. It is very organic. If, for instance, you had to grow a circulatory system inside a dinosaur, you could pretty much just pop this code in.
That's really cool.
Yeah, I wish you could see it. You're getting like 4 frames a second here. I'll put the file. All these files will be online shortly, and it's 24 frames a second. And then it starts growing into what you could, respectably call a cave system. It also kind of looks like brains or intestines. Regardless, it's organic, which is the whole goal of my obsession with cellular simulation. Oh my God! How long has it been?
Wow.
An hour?
Well, including the technical difficulties.
Thank you for sitting through that, Reed. I appreciate it. Let me rerun this again. So what I'm going to do, all those files that we went through today, I'm going to package up and put on my website. I'm going to remove some of the frames because right now it's many gigabytes. But I'll leave like every 10th frame so you can play with it. Like I said, there's a rendering script for Maya, making a rendering script for they're OBJ files so you can load them into anything. My point is that if you, the viewer at home, has enjoyed this at all, you can pay me back by taking this stuff and doing. Andrew Lendon is now linking. Oh, that's a personal note. Okay, sorry. You didn't see that, Reed, but the viewers at home will. Take this stuff. My challenge to you, your obligation for watching this video, is to do something cool with it. It can be anything. It could be as simple as importing this beast into Second Life and giving me a copy of it, or extending it, modifying it, blah, blah, blah. And then you have to create a web page for it, and you have to send me a link to the web page, and I will link to it on my site.
That's so cool. What's the final poly count on the end of there? Because you can. There's the cap of
right. You might have to poly simplify it. I'm sure it's more than Second Life's limits. Yeah. So, like, to actually use this as a cave system in Second Life, I would have to now cut it up into pieces. But I've got that fancy mesh library that will do anything for me, so that's not such a big deal. Yeah. So I don't actually envision bringing this into Second Life fully formed for a while.
Yeah, I don't know how it would do
exactly. Well, as a side note, that library does convex hull decomposition, and I have a feeling, given how hardcore these guys are, that it's probably better than Havoc's. Linden Lab couldn't distribute it with their viewer because they've got some pretty Nazi open source policies. They would.
It's 14 hours.
Well, I don't know. Maybe Linden Lab could. Anyway, they should look at it. But the only other thing I wanted to say before we part for the day is that next time I do something like this, oops, I lost Reed. Sorry, Reed. Next time I do something like this, I would like to invite other people to be in the audience. And if you have any interest in that, send me an email. With that, I'm going to close. Have a good day, everybody. And, whoa, we're losing stuff right and left. Yeah. Better shut down before we get cut off. Okay. Take care, everybody, and have a good one.